Social Networks, Quantum Computing. He is co-author of 5 books and co-editor of more than 50 books and has more than 300 research publications to his credit. He has got 2 patent corporations treaty to his credit. He has been member of the organizing and technical program committees of several national and international conferences, including founding chair and general chair and associate editor of the several reputed journals. He is the editor and editor-in-chief of different journals and also serving as the series editor of various publishers. Sir, it's an honor for us to listen to you and we'll get to learn a lot from this session. I would also like to add that we organizing committee are very pleased with the participation of all the dignitaries. Over to you, sir.
Thank you very much. Let me share the screen first. I hope the screen is visible to you.
Yes, sir, it's visible, sir.
So we'll be just discussing about today some aspects of quantum machine learning, rather, which involves the very interesting algorithm which is generally used for any or in any neural networking paradigm, which is referred to as backpropagation in the classical sense. And we'll be walking through this quantum backpropagation algorithm, which is generally used for different quantum neural network architectures which are coming of late. So before moving on, let me just focus on this particular picture at the left, where you see, and this is actually, you can just think of this situation where two friends are there, and one friend is asking another friend, this is your machine learning system. So the other friend tells, yes, you put the data into this big pile of linear algebra and then collect the answers on the other side. So now the first friend asks him, what if the answers are wrong? What will happen if the answers are wrong? And you are giving some inputs to the system, and then it is jumbling it up and giving you some results which are not expected. So then the other person then replies back by saying that just start the pile until they start looking right. So he asked him, told him that you start the pile, that means make it more randomized or just change the configuration of this entire pile or entire set of linear algebra, matrices, vectors, etc. over there, until and unless you get the outputs which are looking right. So this is the essence of any backpropagation algorithm. So you start with some random configuration over here, some random configuration of weights in the case of a neural network, and then you start feeding data and try to just train this entire neural network with some input and output relationship. But then at that point of time, given it is a supervised sort of training, you know the expected outputs over here. So you compare with the outputs which are obtaining at this point, expected outputs, and the real outputs you are getting, and then you get some system errors which are then used to further refine this entire architecture, entire configuration, until and unless, and this process is repeated until and unless you come out with some answers which are more close to the expected ones. So this is the essence of any backpropagation algorithm. So just to have an idea about the entire picture physically, this figure is quite enough to justify the entire thing. Now the agenda of this lecture will be, because we are dealing with this backpropagation algorithm, we'll be just starting with the basic multilayer perceptron architecture, a small overview of the architecture, followed by the understanding of classical backpropagation algorithm, which actually what is that? Because most of the cases we do actually, our faculty members or the students, they generally feel very shy or shaky about this algorithm because they do not understand the physics behind that. So I want to just make it clear that this thing is not so difficult to understand. Instead of memorizing some equations and using them in your program or implementation, it's better to understand it physically. What actually happens inside a neural network during the course of the backpropagation algorithm, and then following it up with a proposed quantum neuron model. So just having an idea as to how a quantum neural model, quantum version of a neural network or a neuron can be envisaged. Although it is not the only model which you can think of, maybe other models also there, but it is a very simple model. And then followed by the architecture, quantum architecture, which can be formed using these quantum neurons, collection of quantum neurons interconnected by some weights, and then finally ending up with the quantum version of the propagation algorithm, taking or using the understanding which we have obtained from here. So you see the multilayer perceptron is quite well known to all of you because it is generally used for those cases where there are some nonlinear data sets and you cannot use the single layer perceptron or the basic perceptron to classify or demarcate between the different types of data. So if there is a nonlinear boundary, so you require something which is capable of handling the complexity or nonlinearity. So in those cases, you introduce what you do, you introduce some hidden layers in between. So between the input layer and the hidden output layer, you introduce some hidden layers. The number of hidden layers is still the choice of number of hidden layers and the number of hidden neurons is still an open problem. However, we do some sort of empirical analysis, empirical study, and come out with the best possible option. And then these are all connected by weights. You know it, and apart from that, you have a bias over here of a +1 bias. So in the input layer, you have n number of input neurons, say. So actually, the total number of inputs are n+1, using taking into account this bias one also. So these input, whatever you feed over here, they are multiplied by the weights. These are random weights initially, and they are summed up over here. And then a characteristic activation function, either any C-model activation function or any sort of activation function, you can apply over here to get the output which is coming up. So this output which is coming out of the hidden layer is referred to as the hidden layer output. Now the same hidden layer output can be propagated further to further hidden layers, maybe more than one hidden layers may be there, or else you can finally it can be again multiplied by the corresponding weights between the hidden layer and the output layer to get the summed up inputs over here, which are then again applied on by a transfer function, and to get the final output. It is the real output you are getting from the system. And then during the course of supervision, what you do, you just compare the real outputs or actual outputs you are getting with the expected output, because you know the input-output relationship, and you are going to just train this entire system with this input-output relationship. So you just compare between the outputs, and then you get some errors, system errors in all the nodes, and then you just propagate the errors backwards to adjust the system. So you see in all the cases, you have the n+1 input neurons, here also m+1 hidden neurons, so m number of hidden neurons along with the bias. And then finally, you have the L number of output neurons, depending on how many number of classes you are going to segregate the input data. Now, apart from this, so you actually see this is actually sort of bias. Okay, it's sort of a bias which is taken as an input of constant input of 1, and multiplied by a threshold value of theta, minus theta rather. Okay, so these are quite known to all of you anyway. So let me just come up, because I have to make it very fast because the connection over here is not so stable. Anyway, let us see what actually happens in the case of a algorithm. So actually, you see, if you just see this architecture, you could know that means the errors can be calculated over here only, because you have the expected outputs over here and the actual output obtained from the system. So you can calculate, or you can just make a difference, take a difference between the two and get some errors. But what about these outputs which are coming from the hidden layers? So each and every hidden layer also producing some outputs, intermediate outputs. So it is not possible because you do not know what is going to be the expected output at this point, at these points. So that means the errors at the hidden layers are unknown to all of us. That is the main issue. If, however, there was no hidden layer, so it was quite simple, simple and straightforward, because you know the errors. Only this is the error which is going to for the system, and then you can use that error to adjust the weights directly from the input to the output layer. But here, since there are a number of hidden layers in between, and you do not know the intermediate output, so that is the problem. And also, not the intermediate actual expected outputs of the hidden layer. You do not know. There is no idea about that. So that is why you do some sort of what is referred to as the back propagation. That is to propagate these errors in the backward direction to get the error, compute the errors over here, and then using the errors over here, actual errors, you compute the errors over here, and then using those errors again, you propagate it again further in this direction, finally, until and unless you reach the input layer. So by dint of this process, what you do, you go on adjusting the weights of all these weights and also these weights. Okay, this is the philosophy. That is why it is referred to as back propagation. Why you are back propagating? Okay, because the standard gradient descent algorithm is not sufficient enough to compute the errors of the entire system, because what I told you just now, the outputs of the hidden layer is not known to us. So that is why you do not also know the errors of the hidden layers. So that is why you have to do some sort of manipulation in terms of the errors obtained at the output layer, and propagate them backwards so as to obtain the individual errors at the individual hidden layers and propagate it further until you reach the input layer. So that is the philosophy over here, but then it will be quite clear if you just go to this particular diagram. So I'm not going to the details of the text over here, just to have the understanding of the entire backpropagation algorithm. So actually speaking, because we have all learned neural network, because all of you once who are involved in this particular business are very interested in learning how neural network works, but then you do not know what is actually going on inside physically inside a neural network. So a neural network looks like, in fact, in any book, it will look like a circle like this. Okay. Actually speaking, you can think of the neural network to be composed of two compartments. So this is the input side, and this is the weight coming out, and our output side. Input side, output side. Okay, fine. Input side and output side. Some processing summation is going on, talking over here, and then some activation functions also used over here. So let us suppose that this neural network actually contains, or rather comprises, two compartments like this. So now, given this knowledge, let us suppose that it is a very simple form of the entire architecture, but just only a snapshot for the better understanding. So let us suppose that we are dealing with these two: hidden layer jth neuron. So jth, the neuron of the hidden layer, and output layer kth neuron. Kth neuron is output layer, and the connection between them is like this in the forward direction. This is the forward direction propagation. Okay, and this is the backward direction propagation. Okay, if you just go for moving or rather flowing information in the backward direction, what will happen? Because we do not know about that. So you see in the forward case, what actually you do, you give some inputs xi. Okay, input coming from the xi, suppose, and then what it actually does, it takes up, because these are actually the inputs which are coming from the input layer, say, they are actually multiplied by the corresponding weights over here, wij, isn't it? These are all weights. Okay. So actually what we are doing, you are taking the summed up product of this wij and to xi over all I, number of inputs I. Okay. And then what you do, you apply the function, activation function, to get the output of the hidden layer aj. Now, since each and every individual single neuron or the node is composed of two compartments, so when it is calculating aj, it always also calculates the aj dash, that is derivative of aj. Derivative of aj is calculated and stored in the other compartment for the time being, which can be used afterwards. And then what you do, you then propagate this aj, which is output, which is coming over here, but the aj just is stored over here. It is left undisturbed. So aj is coming out. Again, what you do, again some sort of weights are there, wjk. Why jk? Because you are from jth neuron to kth neuron. So wjk is there, weight is there. So again, what you do, you just go for a summation of the wjk into aj, and over all number over j number of neurons in the hidden layer, and go for the function f. And then you get bk. Bk is the output of the output layer. Fine. And simultaneously, since it is composed of two compartments, it also calculates bk dashed, derivative of bk, and store it somewhere in the other compartment. And finally gives out bk as the output, where you can do some sort of comparison with the actual output over here. Right. Now, this is the forward part, quite simple and straightforward. Now, let us see what actually happens when you try to move information or flow information in the backward direction. Say for the time being, let us suppose that this particular neuron, output neuron is fired. Okay, fired means it is going to generate a state of 1. So if I suppose that that particular 1 which is generated over here is being propagated back in the backward direction, you are putting or feeding the output layer with a 1 or the neuron status in the backward direction. Okay. So what actually happens over here, you see the same thing is written over here. The same thing over here is written over here. There's no change. And again, there is no change over here. The same thing. So now this 1 which is coming inside the output layer neuron in the backward direction gets multiplied by the derivative bk dashed and produces bk dashed. Bk dashed into 1 is equal to bk dashed. So the output of the output layer neuron in the backward direction is a multiplication of the input coming in 1 and the derivative of the output layer which was stored inside previously. So it comes out to bk dashed, and again this thing is same, and this thing is same, and this thing is same, and this thing is same. Now again bk dash gets multiplied with aj dashed to yield bk dashed aj dash, which is coming out as an output of the hidden layer. So now your position, you see in the previous case when you discussed about the backpropagation, why it is required, because we told that you are not in a position to understand what is there going to be the output of the hidden layers. Now you know, now somehow or other you are now in a position to get the outputs of each and every layer like this, although in the backward direction. But these things are not being realized in physically in all the books. But anyway, it is a very good treatment I found in one of the books. Anyway, let us move forward. Now, what actually happens, you see, now these things are quite common to all of you. So you see this part. So bk is equal to this function of this part. So using a sigmoidal activation function of the form 1 plus 1 e to the power minus lambda into x minus theta, something theta is the threshold, and this is the, we already az into wjk, and this is the slope of the function over m number of neurons, and so you get this part. This part is the bk output of the output layer like this one. Now you have to compute the bk dashed. How bk dash is coming up? It's quite straightforward, because for this particular function, sigmoidal, the derivation is quite simple. You will get bk dash actually comes out to be bk into bk, 1 minus bk. These things are known. These things are known, and you know it is there in the books. So you are getting, so actually speaking, so bk dashed over here is actually bk into 1 minus bk. Okay, fine. So now this is you calculate the error. Now regarding the error which has been calculated over here individual outputs coming up, not here only. So it is actually given by, so bk is the output which is coming out, actual output, and dk is the expected output. Say, you know, the expected output is going to be there. So you compare that, take a square, because for eliminating the negative part and then going for a square root. Half. So mean, you are taking a mean. So then what you do, mean square error. So you, for a p number of patterns, you get a complex expression like this, but the basic part is same, bk minus dk whole square, half and over for p number of patterns and for l number of neurons. So you get the total error over here, summation. Now you can apply the, in any case, in the case of a single layer perceptron, you should have applied the gradient descent algorithm, I told you, because it was quite simple, because only you have 2 layers are there. But here you cannot do that, because you have to just go on propagating the error also, because in the previous case, you see, you are propagating 1 in the backward direction. You found out that this input gets multiplied by the derivative of the output, and then again the derivative coming up, this product coming up is again multiplied by another further derivative to get the product of the derivatives. Okay, so what actually happens, what will happen if you just go on trying to move the error in the backward direction, which is actually done in a backpropagation algorithm. So this picture will give you the entire thing at a glance. You see now, previously told that the neuron is composed of 2 compartments. Actually speaking, it is composed of 4 compartments. 4 compartments. One part is computing the output, summation of wij, etc., all these things into multiplied by f, applied by the activation function. This is the derivative of this output of the neuron. This is the error at that particular neuron, and this is the derivative of the error. Actually, neuron houses 4 compartments, and each and every compartment is actually filled with information, which is actually used in a backpropagation algorithm. Now you see, just come up over here. So this is just, let us consider the output layer kth neuron. This is the kth neuron as a whole. This is the kth neuron as a whole, which is composed of 4 compartments. Here 2 and here 2. So you know this is computing this part, j is equal to 1 to m w j k a j, which was shown in the previous figure, bk. And bk into 1 minus bk is the bk dashed, already you have seen. So it is storing the output, derivative of the output and the output over here. The output is going to come out over here, and then what you are doing, you are just computing this error, bk minus dk. Dk is here, and then you are comparing dk minus bk or something like that, and computing the error for individual nodes. For the kth node, ek. Then what you do, you go for ek dashed. You compute the ek dash also, which is given by very simple, bk minus dk. If you just take the derivative of this, you will get bk minus dk. So ultimately, a neuron is housing both the derivatives of the outputs and the errors. So now what you are doing, so you are getting there is a position. Now in the previous case also you saw that since we already discussed in the previous figure that it is not possible to know the outputs of the hidden layer, because these are hidden layers, hidden in the literal term. But now we have found out a way to find out what is there inside, what is going to happen over here, because we are getting this output if you just propagate it backwards. So similarly, since you are not able to understand what is there going to be the output of the hidden layers, neurons, so we are also in darkness regarding the errors. So now you know that given this situation, you can now propagate this ek dash rather, to get the errors at the individual layers also. So you see what actually happens when you go for the backpropagation. So during backpropagation, what you are going to do, you are going to propagate this error actually to adjust the interconnection weights. So what you do, you are going to propagate ek dash, not the ek dash. So ek dash comes over here in the other from and one set of compartments to another set of compartments. So it gets multiplied by the derivative bk dashed. This part will remain unaffected. Okay, this part will remain unaffected. So only the derivatives will get multiplied. So what is actually coming up over here in the backward direction, ek dashed into bk dashed. Similar to the case which you showed earlier in the case of a input 1 being propagated backward. So ek dashed into bk dashed. Again, so you see for this particular hidden layer neuron, so ek dash is bk dash. Again, these are all the number of weights which are in the forward direction. For the time being, since you are throwing information in the backward direction, the weights are going to be aligned in the backward direction as well. So for example, if it's suppose that this ek dash into bk dash is going to be propagated here, so it is going to be multiplied by wjk and all w over here, all the weights over here. So similarly, what is going to happen over here? So in this case, it is quite straightforward. Actual output and the actual output we are getting and the expected output. That is the error at the output layer. But here, what we are doing, similar sort of computation is going to take place over here, because this ek dash bk dash is going to be the input to this hidden layer neuron in the backward direction and multiplied by wjk. So wjk into bk dash into ek dash, summation of k is equal to 1 to L number of output layer neurons. All these weights will come up over here. So you will get ej, that is the error you are getting at the hidden layer, which was unknown previously. So we are getting the error of the hidden layer, and simultaneously vis-a-vis you are doing the ej dash, computing the derivative of error. What for? For getting that of the other layer, which other hidden layer may be over here. So again, ej dash is going to be multiplied by aj dashed, only aj dashed. And what is coming up, and again it is multiplied by wij, and again you are going to do some sort of computation. So you are now in a position where you can understand or you can get the errors also at each and every individual hidden layer neurons, which was not possible earlier. That is why we resorted to backpropagation. So this entire mathematics, now you see what in any neural network book you will see. So these sort of equations actually are there, but you go for memorizing them. And in the course of time, what actually happens, the students also feel very, very actually afraid about this, how to understand, how to memorize, but do nothing to memorize, just to see simple mathematics are there. And if you just put these equations together, you will get this. You see all these components over here. bk minus 1 minus bk minus dk, aj multiplied by aj, all these things are over there. And then ultimately, finally, what you do, you go for propagating all these things in the backward direction, and finally you come up with this complex expression in both the cases. In not only in this particular case, ek dash you will get, and also you will get ej dash. So similarly, you can get another set of errors if there was another hidden layer here. So in this case, you see, ultimately you come up with this complex expression of this form. All these components are there itself. You see bk into 1 minus bk minus dk, wjk multiplied by that into a into 1 minus j means aj dashed actually. And then finally, if you go into the input layer, you will be multiplied by the input over here also. Because in the input layer, you are not supposed to go for any sort of computing the summed up product. So input layer is only giving you the xi. So it is multiplied by xi. So ultimately you get, and then you multiply the entire thing with a mu of the learning parameter. So you get this one for the input to hidden layer, and this one only for the hidden to output layer. In the hidden to output layer, we will not get any xi, because xi is for the input from the input neurons. So it is only corresponding to the part, very simple, bk minus dk, error derivative, bk into 1 minus dk, bk dashed, and ajk is for the input output of the hidden layer. So in this way, you have to do, and then what you do, go for weight adjustment, wjk previous one plus mu learning parameter into the expression for this number of neurons in the hidden to input output layer, and this is for the hidden input to hidden layer. In this way, the weights are adjusted, and you see these two expressions are always there in a neural network book, which is describing backpropagation neural network. But I'm afraid that it is quite obvious that you will not find this type of treatment in any book. This is quite very interesting treatment. I will share you the slide. You can go through it. And then, given this background, because the objective of this particular lecture is based on the quantum backpropagation alone, so let us see what actually quantum computing tries to contribute in this particular field and make it more easy or rather more efficient, etc. All these things. So because you know this, I already, it is also a FDP on a quantum computing. So all these things are very well known to you, quantum computing, what it is, what are qubits and what are q gates and all these things, and what are the superposition state and all these things. So these things are quite known to all of you. This is the unitarity constant, unitarity criteria that Cj whole square, sum of all the probability square will be equal to 1. So this is a qubit or Ket0 and Ket1 state. So these things are known to you, all of you. So now, just hold on. Yes, fine. So these things are known. Also, you know this. What is actually what is the structure of a rotation gate, and different types of gates are there, including Hadamard gate, Fredkin gate, Toffoli gate, and all these things. So why actually you are putting quantum rotation gate over here only, not all the other gates? Very interesting. So if you see, look at the quantum, because this is a rotation gate, this matrix forms the rotation gate. And if you take a qubit, and just qubit can also be represented as a column vector of the alpha and betas, that is the amplitudes, square root of the amplitudes, probability amplitude. And then if you just multiply this matrix with the vector, if you multiply matrix with a vector, you get a vector. So a new qubit will be generated. Qubit in different states will be generated. So actually speaking, so if this particular qubit has a phase angle of say phi, so a qubit can be represented as a wave function. If the wave function is the phase of phi, so and if it's multiplied by this, so it will get a new qubit with a phase function of phi plus theta. So actually speaking, what you are doing by means of rotation, you are actually adding up the phases. So all of you know that from the childhood that multiplication is the shortest process of addition. So here also you are doing multiplication actually to add up these two things. So why this is at all important? Because you see what you are doing actually, you are having a initial qubit of a phase phi with a rotation with a particular rotation in the Bloch sphere. Now what we are doing is applying some rotation over there, rotation on the qubit. So for example, this is the Bloch sphere, say. So a qubit was initially here, a single unit vector, and you are by the means of alpha theta, you are going to either manipulate theta or rather apply theta to rotate it in this direction or in this direction, depending on your choice, depending on choice of theta. Why actually you're doing that? You actually first of all you're manipulating this one, pretty fine, and you are trying to make this qubit align either with the K0 axis or the K1 axis or the K1 axis, whatever it is. So that means the probability of getting anybody, if you are choosing theta in such a way that it's going to be aligned closer to the K0 axis, the probability will be higher for this to yield an output of 0 upon measurement. Similarly, in the case of 1, if it is aligned in such a way that the probability becomes greater, so it will be after measurement will get a 1. So that is the objective over here, and this quantum rotation gate is actually used in those situations where you require some sort of multiplication between two quantities like that. For the timing, take it as it is. With a qubit and another quantity, if you want to manipulate by means of multiplication, you have to use a quantum rotation gate to manipulate the entire qubit in a particular direction. So how this actually quantum rotation gate is coming to our use? Because in the case of a neural network, if you go back, you see over here. So actually speaking, these are the inputs xi coming over here multiplied by the weights over here. So we are multiplying xi x into w. Some sort of multiplication is going on. So here actually multiplication means what? You are manipulating or rather modifying x with some factor w, weight factor. So if let us suppose that in the case of a quantum, you can also think likewise. You can implement or you can represent this weight by rotation gate, and this is a qubit. So you are going to manipulate the qubit or modify the qubit by means of a rotation gate. So the weights ultimately can be represented as rotation gate, and the inputs can be represented as a qubit in a quantum computing architecture, quantum version of the architecture. That is why rotation gate is quite relevant in this present context. Now, let us move forward. Now, these things are quite known to you. I'm not going to deal with these features of quantum computing and all these things. So let us move to the actual story. So you see, now given all this background, like the backpropagation, neural network, and this rotation gate, qubit, and all these things, so how you can just put them together to form a quantum neuron. Quantum neuron, which is a building block of a quantum backpropagation neural networks, because we are dealing with quantum backpropagation for a neural network. Okay. So you see the same type of picture is actually here. In same case in the case of a classical case, but here the inputs are in the case of qubits. Ktex1, Ktex2, Ktex n number of inputs and a bias of -1. This is the bias input, okay? And then along with that, these are the weights, individual corresponding weights, which are represented by rotation gates with rotation theta 1, r theta 1, r theta 2, r theta n. And this is a fixed another parameter r lambda for this particular bias input. Okay. So these actually ultimately the rotation gates which we are discussing now have been put over here to form to represent the weights, connection weights. And these are the qubits coming in. So what actually happens over here, you see the similar expression, you are multiplying the rotation, individual rotation gates, rather applying the rotation gates on these qubits. So xi is the gate xi, which is being applied upon by the rotations r theta I, or I is equal to 1 to n, whatever it is, given the number of inputs over here. And what you are getting U. U is the output. That means output means that is the net factor. But before application of the transfer function, because they have not applied the transfer, only the summed up and the product part is there. Summed up summation of the product part is there. And then what you do, you just apply this in the second compartment of the neuron. Similarly, here also you have two compartments. In the second part of the neuron, what you do, you go for, because if you just remember this neural network compares the two compartments, the summation part going on over here and the functional part coming over here. So this is the functional part. So then what you do, you just take the argument of the U, because it is going to be a complex number. You take the argument and then you apply this G delta. Delta is a parameter, reversal parameter. We'll be discussing that in detail later on, which is a characteristic parameter of this characteristic activation function, maybe either a quantum sigmoidal activation function or quantum any quantum transfer function. So G delta is representing the sigmoidal function over here. So ultimately what you are getting Y. And then Y can be represented in some functional form. For the sake of convenience, we'll be discussing that. Finally, you go for a quantum measurement over here and then finally get the output, classical output, because at the end of the day, you have to have the classical output, because the novice user or any user cannot understand quantum outputs. You have to go for some quantum measurement. So this is the overall picture using all the concepts which you have just understood. And then see what actually happens if you just go on aggregating or just putting together different types of these blocks, multiple number of blocks to form an architecture like this. So before going to that, you see the same thing has been described over here. Here xi the qubits, gate xi the input qubits, r theta is the rotation gates, lambda the input bias, because lambda actually r lambda into multiplied by 1 will be giving you multi minus r lambda. And then what you do, you just define this complex number e to the power ix in the form of functional form for the sake of easier representation. And then this thing I already shown you in the previous diagram, r theta I applied on gate x1, for example, this would be xi. And then this is the f lambda. F lambda actually, what is that? This is the bias part or the threshold part. In the previous case, in the class of classical neuron, you have theta. Here it is minus f lambda. Why f lambda? Because the lambda part is coming over here out of this input minus 1. Okay. So, and then what you do, you go for applying this G delta, which is a sigmoidal function. You see same expression. You know the expression of a sigmoidal function 1 by 1 plus e to the power minus x minus theta by lambda. So see same thing. The delta part is actually representing the characteristic of this particular activation function. In this case, the sigmoidal activation function determining the slope and all these things. The parameter. It also referred to as the reversal parameter. So then what you do, you get the final output over here, and then you have similarly in the case, instead of expressing any complex number in this particular form, you are also expressing y in the case of this fy, which is actually e to the power iy. Then you go for some measurement, quantum measurement like this, qm, to get the classical outputs. So you see, if you just go on, so these things are quite known to you, how the inputs are being ultimately transformed to quantum domain by applying a phase transformation of pi by 2 to the real input xi. And then you get this part which is coming out to the phasor factor, and then you go for the. Now the interesting thing is that since you are dealing with a complex number, there are two possibilities. One is that you treat or use the real part of the entire expression for computing the output, or the imaginary part. So in either case, you will get two different results. Not necessarily you will get the same result, but in this present context, we have used you have assigned the 0 part to the real part of the expression, K0 to the real part of the expression, and K1 to the imaginary part of the expression. That means you are more interested in handling the real part, not the imaginary part. If it would have been different, in your case, you could get different outputs altogether, because it is a random system, you know. Now you see the network architecture, how it comes out to be. You just put different forms of the different the quantum neurons and just put them together and can interconnect them with different rotation gates like this. Rotation gates. These are the input qubits. get alpha 1, get alpha 2, maybe other also are there. Then this is the hidden layer, get beta 1, get beta 2, etc. All these things. So these are coming inputs coming over from here, 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 and these are multiplied or they're applied on by the quantum rotation gates individual psi. And then again, some quantum rotation gates representing the ways to get the beta over here, which is another set of, say, another set of hidden layer is there. And then you find it is output layer. This is the omega 1, and then you get some either get psi 1, get phi 1 or get phi 2 as the output in the output. And then you go for some, this is the what you are getting, then you go for taking a measurement over here, you get some classical output, either 1 or 0, or because now 1 or 0 or any other output, then you go for comparing with the expected output, and then you calculate the error, and then you go for moving the error backward to adjust the weights. The mechanism of the adjustment of weights already has been discussed with you. The same thing takes place over here, but with the exception of the real imaginary part, which is involved in any quantum computing operation. So now you see that the interesting thing is that in the previous case, if you just go back and for any neural network, you see, you saw that just to go back. You see, why actually you are not getting the expected outputs over here. Why there is a difference, or why the expected or actual outputs are differing from the expected outputs? Because of the fact that you may wonder, because you are giving the actual inputs, there is no error in the inputs, and why you are getting errors actually? Because of the fact that the weights initially are randomized. All the weights are randomized. So if you think closely, that these weights, random weights are the actual culprits. Are the actual culprits who are creating the entire mess up. They are creating the error, they're introducing the error. So you have to that is the entire philosophy behind the learning process. You start with the random weights. We do not have any information regarding the input-output relationship, and after some sort of iterative procedure, using backpropagation algorithm, adjusting the weights until the weights come out to a particular configuration, then which is aligned with in such a configuration that after that, if you get the inputs, the same set of inputs, you will get the outputs which are very near to the expected ones. That means we are going to adjust the weight. So because the weights are the actual culprits over there. That is why what you do in any neural network and architecture, while computing the error derivative, we go for taking the derivative of the error with respect to the weights. Okay, but here actually you see AJ is the input. AJ is a constant factor. You cannot always ignore that. But actual culprits are the weights. So you have to take the derivative of error, because errors are coming mainly due to the weights. So we take the variation of error, negative gradient of error with respect to the weights. But if you, in this case, however, if you go to the quantum computing counterpart, you see here the three different parameters. In contrary to the previous one, where only the weight was the only culprit, here three culprits are there. First is the phase parameter of the weight connection, that is the theta. There is a theta, angle theta, which we are using over here. The angle theta rotation gate, which we are using. Pardon? Angle theta, different thetas which you are using over here. You do not know the theta. That means you do not know the actual theta, which will be going to give you the exact output. So these are random in nature, and by means of trial and error, you go for finding out the best possible alternative. So this is one of the factors which is going to introduce some error. First of all, so this is the phase parameter of connection theta, and threshold also lambda. This threshold lambda which is used over here, you see R lambda. Again, it is a rotation gate. Again, you do not know the exact lambda. So you start with any particular value and go for adjusting them simultaneously. So here also another factor is threshold, and a reversal parameter delta, which corresponds to the sigmoidal activation function delta. Because delta, I told you, delta is defining the slope of the function and all the functional parameters. So of the sigmoidal activation function, you do not know which exact value of the delta will give you the best possible output. So there are three parameters who are going to create the entire commotion of their culprits. So you have to adjust go for the derivative of the weights with respect to all the three parameters separately. So in this particular case, you are going to have the three sets of equations for the weight update for both the hidden to output and input to hidden layer. In the previous case, in the case of classical neural network, only one single equation was sufficient enough. But here will be three sets of equations, you see, because you have to adjust the theta, you have to adjust the lambda, you have to adjust the delta also. See, And the other things are quite similar, because you see what actually happens. You get the quantum version of the inputs, and then what you do, you go for the calculation. You see, you are expressing the complex rotation gates, parameters, and all these things in the form of functional form. What I just told you just earlier, you can represent any complex parameter with a complex function with a functional form like this fx, for the sake of understanding. So here you have to, just for the sake of notational convenience, we have used the, you see, this is theta ij from the ith input layer to the jth hidden layer. This is the theta for the corresponding rotation value, rotation angle. So this can be represented as f theta j, and this is the input which is coming from behind. This is the input. This is one input, also in the form of an fy, a functional form. So that is rotation gate applied on the input, or the qubits actually. These are all qubits, input qubits, and this is the threshold part. Threshold part of the bias part, lambda, R from the R lambda, okay, for the hidden layer H, for the jth neuron of the hidden layer. So these things are there. So what you do, then by means of some mathematical manipulation, you can always represent that in this particular form, because you already have shown, we have already assumed that e to the power ixi is equal to fx. So you can represent that in the form of e to the power I theta ij plus y this one and minus this. So that can also be represented by cosine and sine formation. Cos plus I sine, again cos minus I sine. And then what you do, you just apply this, you just go to apply application of this sigmoidal activation function on this particular argument of UH, this one which you obtain. Output of the, summed up product at the hidden layer at the jet neuron. So you get this complex expression of this type by means of the mathematical manipulation. I'm not going into details, which can be simply represented by this particular form, which had Zh is equal to given by the complex expression like this. So you see the similar form of things generally take place in the case of a UK, that is the output layer. Again, it is JK from the jth hidden layer neuron to the kth output layer neuron. Theta is the particular rotation gate. This is the YIJH, which was obtained previously, this one. Output of the hidden layer. And then what you do, you get this WIYJ, and then what you do, you just go for the corresponding threshold over there minus lambda k like this. What we told is discussed previously, because there's also a lambda over here, there's also bias over here, also bias over here also. So this bias for the output layer. So finally, you come up with this similar type of expression with the exception of this particular notations at the subscript. And then again, you go for this transforming this particular expression in the form of e to the power I, and then the same type of expression, and then you can representing that in the form of a cosine and sine transformation. And finally, then given this UK, which is the summed up product of the output layer, you apply the sigmoidal activation function again G delta K, taking the argument of QK to get the final output of the output layer. And that is also a similar type of expression which you guys already discussed earlier in the form of tan hyperbolic ZK. So ZK is given by complex expression. So you are getting the output, final output of the output layer. Now what you do, use the same sort of philosophy over here, summation mean square error. But in this case, the error is coming out. This is the actual output, which is expected output, and TNP is the actual output we are getting. That is YK. So then you can go for this error gradient, how to compute the error gradient, which is very familiar. You are familiar with any neural networking book, because we're going to calculate the output. So you see the output which is giving you error. That means the output is not coming close to the expected one, TNP. That is why you're getting error. So now the error in the output is actually due to three parameters. Take the first case, you have to take the derivative of this output with respect to theta, because theta is the rotation angle, and you do not know, or you did not know what is going to be the exact theta, which will give you the exact output. So you started with some random theta. So you have to take the derivative and find out the error, which is the error component coming out due to the different theta values. This is one case. Then these are the expressions I'm not going to deal with. And then again, you see, you have to also deal with this. So ultimately, if you come out with this particular delta E, delta theta jk parameter, this is our error, derivative of error with respect to the theta parameter. So once you get that, you can get the new set of theta, adjustment of theta by me using this theta old minus eta learning parameter into delta E by delta theta old jk, hidden to output j to k. Now again, you see, you have to again go for the computation of the error gradient with respect to delta, that is the reversal parameter. Similar sort of expressions can be obtained. Again, giving you a new set of updated delta in this form. And finally, you have to also go for the gradient of E with respect to lambda, that is the bias, rotation angle for the bias, or for rotation angle for the bias, and again giving corresponding equation like this. So three sets of equation for each and every hidden to output layer, and input to hidden layer has not been yet come. For the input hidden layers, you saw chain rule. You already know because you want to compute theta delta E with respect to delta theta ij. But because you know the hidden layers, you do not know anything. So what you do, you take the use this one, you know, and then you go for some chain rule. You also do know this one and come up with this one. This is standard practice. Doing similar expressions like this. Similar expressions like this. Again, same thing you have to do with the lambda for the input to hidden layer, giving you expressions like this. Again, you have to do this in the case of reversal parameter delta also to get the updated delta j, that is for the input layer. So ultimately, you are now coming up with three sets of equation apiece for both the hidden to input and input to output layer weights or the rotation weights, to adjust them accordingly using the backpropagation algorithm. And then you just start all over again with the new set of inputs, and then you go for seeing whether you are getting something closer to the actual expected outputs after quantum measurement. So that gives the summation, although I've done it very fast because I was worried whether the interconnection is going, or the internet connection is going to be stable for all time to come anyway. But just to sum up the entire thing, what are the key takeaways which are going from this lecture? First of all, we have discussed the operation and the architecture of a classical multilayer perceptron with some physical standing, with some understanding of the physics which is going on inside, which is not generally being taught in any book or given in any book. And then discuss the standard backpropagation algorithm, considering different computational parts of the neuron. 4 compartments, we already discussed that, 4 compartments. One housing the summed up product, another the derivative of the summed up product, one housing the error, another the derivative of the error. And then you just envisage the quantum multilayer perceptron by just forming a quantum neuron model. May not be the only type of model which is existent. Other different models can also be there. Maybe this is one of what the models which seem to be very simple. In fact, this model was designed by us only. And finally, extending the concepts of classical backpropagation algorithm to find out to frame the quantum backpropagation algorithm, although the mathematics have been skipped for obvious reasons, but only giving the expressions only giving some idea regarding the need for computing the error gradient in respect to 3 parameters, which are very vital and which are very influential in introducing the errors over there, like the theta, lambda, and delta. So this actually gives a summary of the quantum backpropagation algorithm. If you're interested enough, you can contact me. I could share the slides with you. You can also get the corresponding publication in the net. Also get it there. You can also just contact. If you are interested enough, you can also contact me. So these are some readings which you can get with some information about this. Some interesting papers also here. So thank you, and I'm open to any query from you which you feel like, because I've been very fast, I know, but then I'm sorry. But if at all you have any query like this, you can just ask me. What do you, Joyanto? You can ask your participants if they feel that they have any query on this point.
Thank you, sir. Any queries from the participant? Uh, I hope, sir, there is no question. However, as usual, if you have any queries or question, you may directly contact Professor Siddhartha Bhattacharya, sir, or you can.
I will also share you the slide with you, so you'll get the information over there also. You can go to the
Okay.
details over there also.
Okay, sir. So I'd like to convey my gratitude towards you for your valuable time of sharing your expertise with us. Thank you very much, sir.